Okay, so in this video we're going to take a look at a practical buck converter circuit. And by practical I mean there's an input source, there's an output resistor load type of thing. We're going to look at some of the physical parameters of the circuit, including how to size the inductance and the capacitance according to certain requirements that we may have, as well as we'll look at some of the conduction modes. There's the continuous conduction and the discontinuous conduction mode. These modes, I guess, apply across multiple different types of converters, so it's important to understand where the boundary is between the two modes, how to operate in one mode, the analysis that takes place for each mode, and so on. So we'll start off with something relatively simple, and that is the inductor voltage, because the inductor voltage is what usually, the inductor, I guess, is one of the central components of this entire circuit. But before we jump into that, I should say that we're going to define the duty ratio, as we've mentioned before, as the duration for which, or how long basically per switching cycle the transistor Q is on. That'll be D basically as a fraction of the whole time. So if we mark, let's say, let's say it's this part here. So we have two waveforms here that we're going to draw, which will be the inductor voltage and the inductor current. We can say that this is dt, and then if that was 4 blocks wide, let's make this one 5, just so it's not the same. So it looks slightly different, and we can call this t. And so we'll make this VL, and we'll make this IL, okay? And so, again, to analyze this, you just look at the two different states. So when Q is on, right, you'll have a short circuit here, and that short circuit will basically mean that VL will be equal to VDC minus VO. And for this part analysis, I'm assuming that VO is a pure DC. We'll see later that it's not, but we also will see that the ripples are small, relatively speaking. So we can treat it for this analysis as a pure DC, because we can design it to be basically a DC. So for this duration, it'll be VDC minus VO. So let's say that's VDC minus VO is something like this. And because VDC is greater than 0, and VO is greater than 0, and VDC is greater than VO, we expect this to be positive. So this is going to be VDC minus VO. And here, once the switch is turned off, so if this switch is off, then that means the diode is on. And if the diode is on, this positive end of VL will be connected to ground, meaning VL will equal negative VO. And so negative VO will be a negative value, of course, because we're assuming, we're assuming it's both have to be the same polarity as we saw in the direct converters video. And if you haven't seen that video where we established the entire circuit topology, I'll link that in the description so you can take a look at that, because it's very useful. And so here, this will be minus VO. Now, inductor current. So the inductor current, when you apply a constant voltage to the inductor, is it basically increases rampwise, right? So what do I mean by rampwise? I mean this will basically increase between here, like this, right? And then during this time, it'll go down, and it'll go down also rampwise because it's a constant voltage that's applied, right? And this you can basically deduce from the equation VL equals L di dt. You just solve the integral, and if you have a constant, then you basically end up with a ramp. But what's the slope of this? So the slope here is going to be the voltage applied to the inductor, which is VDC minus VO divided by L. And here it's going to be the voltage applied to the inductor divided by the inductance. So that's what you have there. And this will obviously continue upwards like this, right? So it'll keep going that way. And then we also have here this ripple we can call delta IL. And obviously there is a non-zero average here as well, right? So this, roughly I guess that's what you can say the average would be. So this we can call IL, capital IL. So it's like this sort of like its DC value. And we can first establish that delta IL is going to equal VL delta T over L. And I got this from the fact that L di by dt is equal to VL. in an inductor, right? So rearrange that and then use delta as opposed to d because we're considering a sort of a larger interval. And so we end up with this. And so if you substitute our circuit parameters into this, you end up with VDC minus VO over L dt. Because you know the duration, you know the voltage applied, the inductance you can solve, or if you know, then you know the ripple as well. But the sort of equation or the result here that is very useful to us is this here. So now we can determine the ripple for a given inductance or the inductance for a desired ripple. Now, if C is assumed to be large enough to block the ripple entirely, then that means I.O., the output current, will be basically a DC value, which implies that I.O. will equal the average value of IL. And again, this is a design choice, I guess, characteristic that we can choose. This has nothing to do with inherently in the circuit. If we pick the proper C, then the I.O. will be equal to the average, or the average of I.O. will be equal to the average of IL, and I.O. will be basically purely DC. Okay. The next thing we can look at are the maximum and minimum values, because the maximum here and the minimum here, so we can call this IL max, and we can call this IL min. These are important characteristics as well, because now we know what the maximum current you're expecting in the circuit will be based on this inductor current, right? So we can define, or we can describe IL max. So IL max is obviously going to be equal to the average IL plus 1/2 of the ripple, right? So that'll be IL plus 1/2 of, well, why don't we just write it all in one shot as opposed to writing it in two. So we can say this is VDC minus VO over 2L dt, right? And then you can do the same thing for IL min, but this will be IL minus 1/2 delta IL. And so that'll be IL minus VDC minus VO over 2L dt. Now you'll notice I used the first part for the calculation of the ripple. You can also use the second part, this minus VO over L. This is 1 minus D times T. You can do that as well. And you can also you'll end up with this equation again if you use the conversion ratio, because we know that VO equals dVdC, right? So you can go interchangeably between two different equations if you'd like to. There's no problem with that. So we have this condition, and we'll come back to this in a second because these two, in particular this one here, is important for us. But before we actually use this equation to do anything, what I want to do is I want to look at the ripple on the capacitor, because the capacitor ripple is another property, because or another sort of parameter or component that you can size for, right? So the main things you would pick in a circuit like this is you'd have to design for the Q, or the transistor should be picked properly, the diode should be picked properly, the inductor should be picked properly, and then C should be picked properly. But what does properly mean? You have to have a certain idea in mind what you want to achieve with your circuit. And so to do that, you have to model the behavior of the circuit properly. So if we're looking at the capacitor ripple, then we're only going to imagine or really consider this part of the circuit. We're not going to consider the switch and the diode, because whatever comes from that part of the circuit, we don't really care. We just care about the sort of the way that this side of the circuit interacts. So this is IL, and this is IC, and this is IO. And so in a nutshell, what you have is this is going to be some average plus some delta. If we pick C properly, then we'll get IC being delta IL, and we'll get IO being IL, right? So basically your capacitor will absorb the entire ripple, and you'll filter all of the ripples from getting to the output, and the output will be purely DC. So how do we pick the value that would allow us to do this? The way we do this is obviously the changes in capacitor current will produce changes in capacitor voltage, but I'm going to call this VC. And so we know from physics and elementary circuit analysis, we know that IC is C dV dt. If I take that equation, I expand the time interval that I'm considering, and I rearrange it. I'll end up with delta VC being equal to, well, first of all, it's equal to delta VO, and VO is this voltage here, obviously, because the two are in parallel, right? So, I mean, it has to be equal. So whatever ripple you see on the capacitor, you'll see the same ripple at the output. So if we can minimize the ripple on the capacitor, we can minimize the ripple at the output. But so this is going to be equal to delta IL dt by C, right? Okay, so we have delta IL divided by C, or sorry, delta IL times T divided by C. We know what delta IL is, and what this means is essentially that the capacitor current is equal to the ripple current of the inductor, right? Because we're assuming that it absorbs the entire ripple. And delta IL, we already have an expression for this. We have VDC minus VO times dt divided by L, and then we're going to multiply this by delta T. And the delta T that we're considering is dt, because that's the time for which this ripple equals this equation. And then you're dividing that by L, that's what the current is, and then you're dividing this by C because that's what the voltage is. So we have this expression here, and the next step is we can kind of manipulate it a bit. And so we'll start again here, and we'll say delta VO. I'll bring it to delta VO because I don't really care about C. I want it in terms of the output. Delta VO is going to equal, let's say, VO over D minus VO. And the reason I'm writing it in terms of VO is because you'll see in a second when I write the final equation that we can have the whole thing written as a fraction, or as a percentage, basically, which is usually a really neat and effective way of designing things. If you just consider it as a percentage of the output voltage, which kind of gives you a relative value as opposed to an absolute value, which is which makes your design process a bit more universal. So you have VO over D minus VO, and I got this from the conversion ratio, times dt squared, and we're going to divide this by LC. Now, you can go through and you can manipulate things and you can simplify things a lot, and I'm going to skip most of the steps here because if I don't, it'll take a while, and you can really do them on your own. It's not very difficult. But basically, delta VO over VO is equal to pi squared over 2, 1 minus D, and then FC over F, and then FC is defined as 1 over 2 pi LC. Right? Right. So, if you want to have a 2% ripple, then what you do is you set this to 0.02, and then you solve all of this for the value of C. So you can go through and you can design these converters in many different ways, depending on what your objectives are. But this is one of the tools that you need, along with the delta IL equation that we have here that gives you the ripple current of the inductor. So the last thing I want to talk about in this, when discussing the buck converter, or the sort of practical aspects of the buck converter, and I mentioned that this minimum current would be important to us. This minimum current. So this is what I want to talk about, is the conduction mode, because there's different modes of conduction. So this mode of conduction that we just looked at is called continuous conduction mode. That's called CCM. So this is CCM, and CCM basically implies that the current in the inductor is continuous. It's always on. The inductor is always drawing some current. It's never zero. It's always above zero. So that's continuously conducting, therefore continuous conduction mode. But it's also possible for this to operate in a discontinuous conduction mode. And what that does is that it has periods of, or portions of the period where the inductor current becomes zero. So how would that happen? I mean, if you imagine for a second, this is an average IL, right? So this IL we have here, there's an average value to this waveform. If that average value of the waveform were to start to decrease, then you might, for instance, have something that looks like this, right? And then if it were to decrease even further, you might have something that touches zero and then goes back down to zero. And then if it goes even further, you might have that it goes, well, maybe we eliminate that one that we just drew. Maybe it goes up and then comes down and then it stays zero, right? So the waveform that I've drawn here, this purple one, this last one that I drew, is a sort of deep into discontinuous conduction mode. And the reason we know that is because there's a portion of the thing where it's 0. But before we get into discontinuous conduction mode, you would be right on the edge, right? So that would happen when your minimum current becomes 0. So when IL min, that I've written there, becomes 0, that's the boundary between continuous and discontinuous modes. And so the way we define the boundary is usually by the average current that would result in that value, right? So what do I mean by that? I mean, here, in this case, we see that there's an average current. There is some average current. That average current should be greater than this average current, because in the boundary case, you'll end up with some average current. And the average current that results in the boundary case, where IL min equals 0, is referred to as the boundary current, basically. So I mean, well, you can define it in terms of the inductor or the output. Usually we define it in terms of the output, because the only way this average current changes is if the output current changes, right? Because the whole thing is connected together. So if the output current decreases, then this average current also decreases. And so you have to make sure that there's if you want to operate in the continuous mode. If you don't, then there's no problem. But still, you want to make sure that your output current is larger than your boundary current if you're operating in continuous mode. So maybe we can draw like a waveform here to just sort of illustrate that concept that we just discussed. So if we have a current, and the current goes up, and then the current comes back down here, like this, this is a sort of boundary case, right? Because the minimum values are 0. Now this will have some average current, and this average current that goes from 0 to there, we can call this, if this is the inductor current, we call this ILB, B for boundary. Okay? And if we know that this value here is I max, we'll call it the maximum current. You can call it IL max. We called it IL max. Let's call it IL max again, I guess, just to be consistent. So this will be IL max, right? And that's always IL max, whether it goes up or down. I mean, it makes no difference really. But in this case, I mean, it's actually useful for us. This is IL. And so this here is dt, and then this here is t, right? I've drawn it symmetrically. You probably shouldn't have, but it makes no difference overall to the entire analysis, really. So we know that IL max is something, and we know that IL min is also something. We have equations for both of them. But the boundary happens when IL min equals 0. And so if IL min equals 0, we want to know what is the average current that gives us IL min equaling 0. So the equation for IL min that we had above was IL min equaling IL minus 1/2 delta IL, right? So if I set this to 0, and then IL becomes ILB, then I have ILB is 1/2 delta IL. And I know what delta IL is, so that's not a problem here at all. So I can say that ILB is equal to VDC minus VO over 2L dt. Now in this case, in the case of the buck converter, we know that ILB, not ILB, we know that IL in general, the average value at least, we know that the average value of IL is equal to the average value of IO. That means ILB and IOB are the exact same. So the boundary inductor current is equal to the boundary current for the output. Because when we're comparing them, you have to compare what the average value of the inductor is with the boundary current of the inductor, or compare the average output current to the average output boundary current. So you have to make sure that you're comparing it to the right boundary. You can't compare the output current to the inductor current and say, oh, it must be in continuous conduction mode. You can in this case, but you can't generally. So it's usually easier to, and it's much quicker to calculate the output current, because you just take the output voltage and divide it by the output resistance in a resistive load, for example, and then you know what's going on. Or you have a load that has a specified current. So you know what IO should be, compare it with IOB, and then you know which mode you're in. We'll see when we discuss the boost converter that ILB is not well, yeah, so we'll see that ILB is not necessarily the same as IOB in some of the other converter topologies. But in this case, it is. So to check the mode, compare IO with IOB. If IO greater than IOB, then this is CCM, this is continuous. And if this is less than IOB, then, well, this is greater than equal to, because the boundary is still technically continuous. And then if it's less than, then it's DCM. So in a DCM case, what you would have is, you would have something that looks a little different. So we should analyze the DCM case as well, because it's important to understand what the converter behaves like in DCM, because DCM is actually can be useful. It's not that it's a bad thing. It just means it might seem like it is, but it's not necessarily a bad thing. In fact, for the purpose of control design, DCM operation is actually really good. But there are some trade-offs, and the main one being that you need a larger maximum current for the same type of operation as you would for a CCM. So if this is IL, and we assume that this is now DCM operation, so this would go up, and then it would come down here, let's say, and then it would be 0 for some time. So maybe we make it 0 for some time that doesn't look the same as the other two, and then it would start going up again like this. And so the way we define these regions is this part here, and then this part here. So if I look at this whole thing is T. If I look at this part here, this is delta 1T. And if I look at this part here, this is delta 2T. So during delta 1T, you have this sort of drop, and then in delta 2T, you have this inductor current becomes 0, and then here at T, the cycle sort of repeats itself. But these slopes don't change. This is still VDC minus VO over L. This is still minus VO over L. And of course, this part here is 0, so that doesn't really matter. So how do we make use of this now? We can analyze this to determine the conversion ratio, because the converter is no longer behaving as it was in the previous case. So we can't expect the conversion ratio to be the same, and in fact, it's not the same. So if you were to use the relationship VO equals dVdC, and it's operating in discontinuous conduction mode, you would not get the correct answer, or the correct conversion ratio, or the correct relationship between the input and the output. It changes for discontinuous conduction mode, which is expected since you're not using the entire switching period. There's some fraction of that being used. So how do we analyze this? What we can do is we can break this up into the rising ramp, the falling ramp, and then we can analyze the two together and then kind of start to figure out what's going on. So from the rising ramp, we see that from the rising ramp, we know that IL max is equal to VDC minus VO over L dt. And I'm calling this thing here IL max. Okay, so this is IL max. Okay. And if I rearrange this, then I'll get that D is equal to L IL max times F. I'm going to write it in terms of frequency because we often work in terms of frequency and not periods. This is VDC minus VO. So this is one of the equations that I want to work with. Maybe we can call this equation 1. Okay. Next, from the falling ramp, we see that this thing falls minus IL max, right? So it goes from IL max to 0, meaning that total change was a minus IL max change. So minus IL max is equal to minus VO over L times delta 1T. And then if you rearrange this, you get that delta 1 is equal to L IL max F over VO. And so this is your second expression. And so you can take these two, and we can do some, I don't know, it depends on what you think is fun, but you can do some, I guess, fun stuff with them. But you know then also that the average of this waveform, so again, even though this is, now it's touching 0, it still has an average value, right? So the average of this will be somewhere like, I don't know, somewhere in the middle here. Let's just imagine for a second. And so this is going to be, what do we call it? I guess IL well, we can call it just a capital IL. We can call it IL, like this, right? So we know that IL equals I2, or, well, I call it IO here, right, not 2, IO, and that is 1/2 base times height, divided by the period, right, because the area here. The area, this is a triangle, and it's 0 otherwise. So 1/2 base is going to be delta 1 plus d. T gets divided out because it's an average, time average that is. And then there is here IL max. Now, if I take these two equations, 1 and 2, and I plug them into this IL equation, and I rearrange the equation and I simplify things a bit, then what I end up with is I get an equation that says 2IO over LF is equal to 1 over VDC minus VO plus 1 over VO, and this is IL max squared. And we know what IL max is. We have an expression for it right here, right? So that's not a problem. So we can substitute that in, and then we can simplify it a little bit further. And I won't do the entire steps and all the process here because it'll take forever. But you essentially end up with a conversion ratio. So the conversion ratio we always say is V2 over V1, right? And so in this case, it's VO over VDC, right? But this applies to the general case of a discontinuous conduction mode buck converter. It doesn't have to be this VDC VO type stuff. You have d squared over d squared plus 1 over 4 IO over IOB max. And now what is IOB max? Let me put a box around this first, and then we'll discuss what IOB max is. So IOB is, well, ILB is this thing here. At some point this will reach a maximum. Okay, and the maximum it reaches is according to the value of D. Okay, so you can rearrange this thing, find out what the maximum value that it can take is, and it turns out that if you do all of that and you find the maximum value, this IOB max is equal to VDC divided by 8LF. And so that's what you have here. And I think I've used the wrong color. I think this should be this color. And I feel like, personally, this should be orange because this is an equation, and it's usually a good idea to be consistent with the way you do things. So we have here this discontinuous conduction mode sort of operation of this of the buck converter. Here's what we've seen, right? So now we have this expression here. You can calculate that. You can plug it into there. You can determine what your conversion ratio is. If you're in DCM, we'll look at some examples of how to actually determine which mode you're operating in a practical setting. But for now, to just recap what we did, is we've taken a practical buck converter and we've basically sized its components and we've determined its mode of operation, right? And what do I mean by sized its components? I mean, if you want to your inductor to have a plus minus, let's say, 2 amps ripple, you can calculate the value of L that will give you that. If you want your capacitor, or so you want your output voltage to have a 5% ripple, you can calculate now your C based on the value of L you have that you calculate from this initial thing here. You can then determine what value you need here, right? So this is a sort of design type of equations that you need. I mean, again, we're analyzing it, but that's really where design comes from, is analyzing these types of things individually like this. So then we looked at, this in a sort of broad sense of what it means to be in discontinuous mode and continuous mode and so on. But the main thing we saw is that it's the average current that we're going to compare. And again, we'll look at examples and it'll make much more sense once you see it in the context of a practical example. But for now, we have this expression for the conversion ratio in discontinuous conduction mode. We have the continuous conduction mode that we've already developed previously. If you have any questions, leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.